Hi guys, now we have a similar problem, but now we don't have infinitely long wire, but just this wire with its finite length, L above and minus L above, so the total length is 2L. But now the problem is that lambda, which is linear charge density, is not constant, but it is given by AY. Don't forget, lambda we will take it as dq over dy. So it is given as AY. Okay, so from this we can write dq, which is equal to AY dy. Now the question is, what is the potential at this point? Distance x from the wire. So we would like to find the potential at any point. Of course, we will consider all these lengths, and we have to consider this linear charge density to integrate. So how could we find the potential at this point? So the potential is just dV, okay, dV is just k times dq over r, okay, not r squared, r on the denominator. So we have to integrate this. We are treating the potential at this point that it is produced by just a little bit charge here. We are assuming that this length dy is infinitesimally small, so that the charge dq is considered as point charge, so that its potential is given by this expression. So to integrate this, okay, we have to be careful and we have to handle this dq because we are not used to the charge integration. So this charge integration should be reduced to the dimensional integration. So from this integral we get the potential, which is equal to k is constant dq, but dq is just ay lambda dy divided by r. So this is it. Now don't forget, y is changing when you go up and down. Okay, this angle theta is also changing as before. So that now this is a y integration, there is y there, and then r can be written as a function of r. Okay, so how can we do this? R is just simply square root of, okay, x squared plus y squared. Okay, now x is constant. Don't forget, in this integration, x is considered to be constant because this is a y integration. And now this is not a really difficult integration because we can use the change of variable. If you say that u equals x squared plus y squared, okay, then du will be equal to, since x is considered to be constant, just 2y dy. Now we have not 2y dy, but just y dy, so that y dy should be du over 2. And if you put also this a outside, then the potential will be written as 2k, okay, du over 2. Sorry, it will be just k times a divided by 2, because y dy is du over 2, integral du over u square root, okay, square root of u. But square root of u on the denominator means that it's minus 1 over 2, okay, 1 over 2. When you take the integral of this, you just increase the exponent and then write the exponent, okay, to the denominator, so that the result will be given as minus 1 over 2 or minus 1, okay, plus 1, so you add 1, and then minus 1 over 2 plus 1. So it means that it will be just, the result will be just square root of u divided by 1 over 2, okay, 1 over 2. So the potential will be given as Ka over 2. Now, you remove the integral sign because you solved it already. So the result is square root of u, but u was given as x squared plus y squared, x squared plus y squared, and then the limits divided by 1 over 2, by the way, divided by 1 over 2. So this 1 over 2 cancel this 1 over 2. Anyway, the result is minus L to L. But now what happens? Look, everything is going to be positive inside this square root because everything is squared. Whether you use minus L or L for y, you will end up with the same thing, so that the result will be 0. Okay, Ka. Okay, so if you use upper limit, square root of x squared plus L squared for y. Don't forget, this is y integration. We're replacing y for with L. Minus the lower limit, But the lower limit, if you put minus L square, it's again L square. So x square minus L square just give you 0. That's it. So the potential at this point is 0. Why? What is the reason the potential is 0? Is really hidden here, okay? If lambda is changing like this, as you see, charge is positive here, but negative there. Basically, this is how the charge is distributed. Not only that, but as you go up to the end of the rod and also go down to the bottom of the rod, the intensity of the charge is increasing. So there are more and more charges when you go to the top and bottom, of course, minus and plus. So this is a different problem. Earlier, we just solved the problem infinite long wire, and then everything was just plus. So, but now, as you see, we have finite lengths, but the charge density is changed like that. Okay, so this is it. So as the other problem, we can again find what is the electric field. If exactly we have the same problem, what is the electric field at this point? So let's try to solve this. So now we have again our x and y coordinate system, and then we place our wire there, okay? And then this is L, and this is minus L. This is 0 for y and x, okay? So again, we consider dq there, dy, and this is y, and then the distance is there, okay, r, and this is x as before. So now we have exactly the same thing as before. So if this is dE, then the components of this from here, okay, you have to be careful because dE not, you have to get this angle, okay? If you know this angle, you will get dEx, okay? And also dVy, okay, dEy. So dVy, but probably, I don't know, maybe they cancel each other, or they don't know, they don't. Earlier, dEy's will cancel, was cancelled, but dEx survived, so that we multiply this by cosine theta, because dEx is just dE cosine theta, but dEy is just dE sine theta. Okay, sine theta. So now let's try to find Ex. So if there is an electric field in x direction, so what is Ex? Let's say Ex is given by just k times, okay, dq over r squared. R is this distance times cosine theta. But dq is given as lambda equals ay, which is equal to dq over dy. dq is just ay dy. So it's k ay dy cosine theta, okay, divided by r squared there. So r and cosine theta can be written in terms of y, so that k, okay, a outside because this is constant, cosine theta, but cosine theta is just equal to x over r, but r is given as the square root of y squared and x squared. So that it will be r cube on the denominator, so that a is taken outside, y, dy, and x there, okay, coming from cosine theta, divided by r cube, but in r cube we have to write as x squared plus y squared, okay, cube root. Now this is again the same kind of integral, okay, like this, okay, like that. So we can use change of variable again, say u equals x squared plus y squared, and the u will be equal to just 2y dy, and then we will have now ka, okay, integral y dy, integral, instead of y dy we are writing du over 2, so 1 over 2 du divided by u to the power of 3/2. So it's the cube root of u on the denominator. So since it is u to the minus 3 over 2, the integral is just you add 1 to this one. So minus 3 over 2 plus 1, everything divided by minus 3 over 2 plus 1. Okay, so whatever it is. So but minus 2 over, 3 over 2 plus 1 is just minus square root of 2. Okay, u to the minus 1 over 2. So the result is just 2's will cancel, but you will need a minus sign coming from the denominator, which was minus Ka, okay, u 1 over u to the power of 1/2 or square root of u, and then it's equal to minus Ka 1 over square root of x squared plus y squared. Now the limits is from minus L to L. Again, the same scenario, because you know, on the denominator there is y squared, and when it doesn't matter if you put minus L or L, you will end up with the same thing. So when you subtract, you will get 0. Simply there is no x component. Why? Because the charge distribution was given like that. Okay. So this was the x component of the electric field we obtained. What about the y component? For y component, we have to use sine theta, which is equal to y over r. Okay, y over r. Sine theta is just y over r. Okay, if you put y over r, there will be y square on the top, and then you can integrate. But it may not be really 0 or something, but you can do that as an example later on. Okay, so the only difference between this example will be just replacing sine theta by y over r and then integrate this. And please try to find if it is 0 or not. This is your homework. End of the recording.